won't give a long intro here, Jeremy. I'll let you speak for yourself. But Jeremy Werdell here is the PACE project scientist. Uh, he's he's been the force of nature behind all of this happening for the full development of PACE, and I'm really excited that he was able to come talk to us, and you all can hear it directly from the mouth of the PACE scientists. And appreciate you coming, Jeremy.
I appreciate the invite. Can you see a slide deck now?
Yes, indeed. Full screen, looking
All
good.
right, awesome, cool. Thanks to you and Eli for doing this and all of your collaborators. The invite's nice, but just the fact that you're doing this at all is really important. It uh, it is very rewarding for those of us who have been embedded in the mission for a while to see others take things with it and run with it. So thank you. Thanks to all of you for showing up too. We really, really do appreciate that. So, and sorry, I'm getting over a little bit of a cold, so I'm going to be scratchy voiced for most of this. So, Ryan mentioned, I am the project scientist for the PACE mission. I reside at NASA Goddard Space Flight Center, but I represent, just a couple hundred people who have made this a reality. Um, so with that, talk is really kind of three-ish parts. Knowing that most of you through fisheries probably have a good understanding of ocean color and why we do all of this, but maybe not everybody. I thought I'd really start just way at the beginning. So if it is too rudimentary, too elementary, I apologize. Just bear with me. The first part is just going to go through that, and then the second, third will be a little bit more bookkeeping and what the mission's all about, and give you some examples of products that hopefully you'll bring into your projects over the course of this week. So here we are. We launched just about 2 years ago on February 8th, 2024, from Kennedy Space Center in Florida. Today is, if my math was correct, the 719th day of the mission. Probably more notably is the nice round now number of the 10,000th orbit that happened just before we all broke for the holidays, which is a pretty rad milestone. So really happy to see that. Everything so far has been very rewarding and has been operating nominally. So hopefully that's 10,000 of many, many, many tens of thousands that we get to enjoy from this mission. All right. So as promised, we're going to start in the beginning here. Ocean color satellites effectively operate exactly the way that your eyes do. They make informed measurements of color, and instead of having, the human brain, they've got a lot of electronics and a lot of math behind it that take color and convert it into some interpretation of what you're actually looking at. So, as all of you know, you're looking at crystal clear blue water. Your intuition is telling you, hey, there's really nothing going on here. This is just water with not a lot of things in it. Whereas if you start seeing some green water, suddenly you might be thinking, all right, well, that's not super clear. But green is biology, so there's algae or something plant-like growing in here. This is a productive body of water, for better or worse. Then when you see the brown water, and I'm located in Maryland, so this is kind of what Chesapeake Bay looks like, a bunch of the year, like, all right, well, that might have biology in it, might have other things in it, but there's certainly something resembling tea and suspended sediments. So again, your brain is already doing this, and what we're really just doing is trying to convert this observation of color from space into, some quantification of what we're looking at. And then there's the oddballs. In this case, you're looking at a red tide bloom. You're not used to seeing red water, but yeah, again, it's not normal here. What's going on? Should we investigate further? Just like your eyes, the information from the satellites gets you to the point where you're saying, red, danger, danger, Will Robinson, we should be thinking about what to do next here. So saying this all again, but doing it a little bit more quantitatively, and thank you for Ryan. He provided this slide probably a decade ago, and it's got as much mileage from it as just about anything I can imagine in my career here. But this is effectively a spectral representation of what I just said. You're looking at a Mississippi River Delta from north to south or top to bottom. The brown water near shore all the way to the blue water kind of offshore at the bottom of your screen. And if you're looking at the right here, on your x-axis, you're looking at colors of the rainbow. So, ultraviolet and blue and 400, your near infrared reds at 700. And what I want you to see here is that the intensity as a function of color of the rainbow pretty much changes as the water type changes. And so this is really just the the engineering version of what your eyes are doing here. If we can measure all of these colors and we can see when there's a lot of blue light or a lot of brown and yellow light versus a lot of green light, well, that information can be used to tell you more quantitatively what we're actually looking at in the water. Also, courtesy of Mr. Vandermeulen here, we've got a graphic that for the third time will restate all of this. And so you have happy little photons coming down from the sun interacting with the atmosphere. And effectively, any interaction these photons have is determined by what they're interacting with, whether it's a gas, whether it's a particle, whether it's dissolved material. And it doesn't matter what fluid you're looking at or what solid you're looking at. In this case, it's atmosphere and water, but it could be Coca-Cola, it could be blood, it could be anything, basically have interactions of photons that change depending on your wavelength. So in this case, all these happy little photons from the sun find their way through the atmosphere, interact with the sea surface, and then penetrate into the water mass here. Pretty much photons have two fates. They either get absorbed and turned into heat or something else, or they get scattered until eventually they get absorbed or they reach your eye. So in this case, everything that's in the water column is determining absorption and scattering of all of these happy little photons. And as you can see in the cartoon, that interaction is intended what the cartoon's trying to represent is that interaction changes how different wavelengths of light interact. When you have absorption and scattering of one wavelength versus the other, as we saw in the previous slide, the color actually changes. So the way the remote sensing paradigm works is those photons that are lucky enough to exit the water column make it back through the atmosphere to the top of the atmosphere. Well, now they're observable. And the satellites in this case are acting as our eyes. So you just have these brilliant instruments up there collecting photons and effectively creating a product that is no more than the light intensity at different wavelengths. And in the case of ocean color, typically what we're talking about is something from the ultraviolet into the shortwave infrared portion of the electromagnetic spectrum. So there you have it. That's pretty much ocean color at its fundamental basis. But again, we're still talking about optics here and total radiometry and total intensity. How do we relate that to what we actually care about? Well, you can have various levels of sophistication in your math. We've been doing this for about 40 years from space, and one of the most robust, but also kind of brain dead simple versions of an algorithm that takes optics and converts it into biophysical parameters is this band ratio for chlorophyll A. Chlorophyll A is a photosynthetic pigment, ubiquitous in anything that photosynthesizes, land or ocean. So in this case, your x-axis just happens to be a ratio of blue to green radiances, so measure two colors. We can relate it to the y-axis, which is an observation of chlorophyll A in milligrams per cubic meter. And if you squint hard enough, even though this is in log space, you can see that there is a fairly robust relationship here. If you do this on every pixel, you start making these brilliant maps. In this case, again, you're looking at chlorophyll A, but this is in Chesapeake Bay, where the color bar is really kind of this non-intuitive rainbow, where the purples and the blues are the deserts and the really clear open ocean. Not much going on water, and the reds and the yellows are the productive areas or the highly turbid areas where there are more of the forests and things are going on. Okay, so put that all together, do things for 20 years, and you can create imagery like this. And I would take to the mats anybody who says differently than this being the greatest achievement NASA has ever realized. It is 25 years of watching your home planet breathe. It's a combination of chlorophyll A and land measurements from CWIFs and the MODIS and the VIIRS, 2.5 minutes of your senses compressed all the way up into space, and you're watching the heartbeat of our planet here. So again, the color bars are a little weird when you're looking at the ocean. Purples are the deserts, warm colors are the forests. Obviously on land, it's a lot easier because the forests are in green and the deserts are in brown and ice is in white. But if you know what you're looking at, you can see this heartbeat changing over time. The ocean deserts are expanding and changing their locations slightly. The reds are getting more intense and starting to appear in places that they haven't been seen before in many cases as well too. I find this to be very meditative, something that should be on all of our walls. Anytime you feel a little stressed at work, you just start looking at this. But it's limited. What you're looking at is a concentration of chlorophyll A. It's really informative in terms of telling you total abundance, but it's not giving you a whole lot of information without really specific local knowledge about what phytoplankton community is behind the scenes. And that's really where we want to go. And that is the fundamental promise of our little mission called PACE. So the biggest contribution in terms of, aquatic biogeochemistry that PACE makes is this move from multispectral radiometry to what we'll call spectroscopy here. So on the left, you're looking at our heritage missions at NASA, CZCS through VIIRS, and the different little slices of color here are intended to demonstrate where the wavelengths are placed on the satellite instrument. So when I say multispectral, what I'm saying is we're collecting spectral information in multiple different places, but you'll notice that there are gaps. And no shade to any of these heritage instruments. Those wavelengths are very, very intelligently placed to retrieve a phytoplankton signal from the background of everything else going on. But there's a lot of information in those gaps. And that's where PACE and this hyperspectral universe of spectroscopy comes in. It's a continuum measurement of color without any gaps. So give you one example while you care. A place where I did a bunch of my PhD work is the Northern Arabian Sea. And there's a very profound community shift that has been ongoing for the past 2 decades or longer or so. And that shift has gone from a traditional, fisheries-based phytoplankton community of diatoms into a heterotrophic dinoflagellate called Noctiluca, and it's changing the entire base of the food chain. So what you would see with a multispectral instrument like VIIRS is that plot right in the middle of the left hand of your screen here. What you're looking at is wavelength on your x-axis and a version of what the satellite would see on your y-axis. The traditional diatom fish food version of the world are the black dots. The big bully of Noctiluca coming in, which is more of a turtle and jellyfish-based system, are the red dots. And if you're looking at VIIRS in the multispectral universe, you can see there's only really one unique piece of information right around the green wavelength of 550 nanometers. But what PACE OCI sees, this is an old slide, not will see, you can see all of those dots filled in. And through that green part of the spectrum and in the blue, there's a lot of information that can be used to distinguish these two species. And we just can't do that with our heritage instruments. So given the capability of PACE for this hyperspectral universe, plus a lot of other things that it can do, we're really starting to enter a renaissance of our ability to really tease apart far more aspects of the Earth system than we've ever been able to do before. Okay, so driving that point home one more time. On your right-hand side of the screen here is basically the analogy to that beautiful pulsing chlorophyll map I showed you a few slides ago. On the top, you can see modeled phytoplankton communities. The 4 colors represent 4 different communities, and there are a lot of beautiful whirls and swirls, and it is amazing imagery, but it's modeled imagery. There's no real direct observation of this, and direct in quotes, of course, because again, we know we're relating optics to biogeochemistry here. The satellites aren't reaching into the water, measuring anything. And then the bottom of the screen, just to ensure that everybody knows the PACE acronym is not just plankton and ocean ecosystem. It also has aerosols and clouds in it. You can see something very similar, but in this case, it's for atmospheric aerosol speciation. And what's really important about this mission as well, particularly given the 3-instrument complement that I'll show you later, is we're not only trying to get to community structure of phytoplankton, but species structure of atmospheric aerosols as well too. And to move from this modeled universe into direct observations so that A, we can improve our models, and B, we don't have to rely just on models which we know, don't always agree with each other. And so given all of the objectives of the mission, what we ended up boiling it down to is this beautiful, beautiful girl here in the center of your screen. She may not look much to you, but she is perfect in every way. It's a 3-instrument observatory. The big one on the top is cleverly named the Ocean Color Instrument. That's the primary instrument. I say cleverly named because it is capable of far more than just oceans. It is highly capable for terrestrial, cloud, and atmospheric aerosol retrievals as well. This is a hyperspectral scanning radiometer that runs from the ultraviolet into the near infrared in 2.5 nanometer spectral steps, 1.25 nanometer spectral steps in certain parts of the spectrum as well. It also has 7 discrete shortwave infrared wavelengths. There have been other hyperspectral missions where we come in to be the best and the brightest right now is the 1 to 2 day global coverage. And that's what's really, really important. So we've never had these eyes in the sky, hyperspectral signals on 1 to 2 day global basis where we're just filling in the gaps over and over and over again. Now, I hope during your journey through FishPace, you will also consider use of our small but mighty polarimeters. We have a pair of them. They are also passive radiometers, just like the cartoons that I showed you before, but they do two things in addition to what OCI can do that are super cool. One, they measure the polarized state of light, and two, they do this at multiple view angles. So instead of an OCI-like instrument, which is only looking in one direction all of the time, these two polarimeters are looking at multiple directions, and the combination of the polarized signal plus the multiple view angles is really, really profound when you want to start studying microphysical characteristics, layer heights, whether you're looking at clouds above aerosols, aerosols above clouds, how thick plumes are, on top of everything else that you can do with the microphysical and thermodynamic characterization of our atmosphere. It's really, really remarkable. And my challenge to all of you is to take everything that the atmospheric community is learning and apply it to hydrosols instead of aerosols. Because I think one of the renaissances that we will start emerging into is the use of multi-angle polarimetry for hydrographic and aquatic optical property retrievals as well. Anyway, briefly, you can just look at the details on the side here, and hopefully you have access to my presentation. But the takeaway message is that the polarimeters complement each other very well. You know, they're only the size of maybe a tissue box, but they do complementary things in a really beautiful way. One being multispectral but hyperangular, the other being hyperspectral but multiangular. So please, please play around with them. There are so many papers to write using polarimetry. All right, so now we're going to get into just a teaser of, some of the products that are out on the street and available for your use. In this case, you're looking at phytoplankton community structure in the Southern Atlantic Ocean from the Moana algorithm. The left is just a true color or false color image. This is what you would see if you were looking down at this body of water in South America from floating at the top of the atmosphere. And then on the right, you can see three different colors representing three different um, picoplankton communities. So these are the really, really small guys here. And what I always find amazing about this kind of imagery is if I'm looking at the dead center or kind of upper right-hand corner of the RGB image, I don't see a whole lot going on the left-hand side, but a lot of things tend to pop when you start looking at the Moana output here. And that to me is really profound about the ability to use this hyperspectral signal to really make the invisible visible. And that's ultimately what the promise of this mission is. And most of the Earth science missions that NASA and NOAA and our colleagues do, we make the invisible visible. So in this case, you're also looking at Moana, but now you're looking at a climatological time series. I mean climatological because these are monthly averages, but watching again this first kind of glimpse of not just watching your home planet breathe, but watching the biology behind it ebb and flow changes is something new. This isn't hot off the press anymore. It's been out for a few months, but again, nothing like it's been done before. So please take these data and play with them. Okay, since this is a fisheries-based audience, just pointing out that there is already a lot of support for the use of these kinds of data in fisheries. In this case, it's a testimonial from industry. Ralph's has been playing in the ocean color arena since I think I started back in the late 90s. But they've certainly found value in these data to support their industries and fishermen. I remember on the road up to launch, I actually spent a fair amount of time talking to representatives from different fishery organizations in states like Maine that wanted to use this kind of information as layers in their fish finding and hydrographic systems. So hopefully there are some practical applications of this that will continue to emerge and become valuable. As you know, not all phytoplankton are your friends. There are some actively trying to kill you. Here is an example of using an ultraviolet band to get to Lingodinium, west coast of California. Some emerging work. In this case, we're looking at the West Florida shelf here, looking for a series of different phytoplankton communities in the optically complex waters that are here. And again, I'll go fast through these because one, you're fisheries experts, you know all this. Two, I assume the slides will be available. And three, maybe you've seen this before. But what's important here for me trying to not sell you on this, but convince you this is a great tool is that all of these slides are really dialing into a different community. And again, that's where the power of this instrumentation comes in. In this case, you're looking at a different version of Carinia. In this case, it's in the west coast of Australia. And then, of course, inland waters as well, too. We've started converting this cyan project and cyan retrievals into PACE ecosystem as well. And I'm excited about that because there's additional spectral information that I think might allow drilling in even deeper into the comings and goings of these harmful blooms in inland waters. Now, yes, we have a bigger footprint than what this project, if you're familiar with cyan, uses now. It's using Olchian Maris, which has a 300-meter footprint. But now you have a 1 kilometer footprint from PACE OCI, but a ton of extra spectral information. So there's a little bit of a playground here, I'm hoping. But again, this is all work for you to be doing. And then last, one of the things that I've actually really enjoyed about the mission is the discovery of capability that we didn't actually think of before we got to launch. So these are some results that really aren't per se fisheries related, but are also really important and also included in this presentation to try to stimulate for you. There's so much about this mission that we will grow into. The discovery is ripe and available. And I'm surprised every day by, a phone call and email saying, hey, I think I could do this, and I didn't think I was going to be able to. And what you're looking at here are two different ways of looking at the impact of the LA wildfires from a year ago. On the top, it is looking at two different plumes of aerosols. Some are smoke, some are dust from one of the polarimeters on PACE. And then on the bottom is the use of OCI to classify burn severity and burn ratios as well. And while not all of this is exactly new information, especially the burn severity, where I think there's a lot of opportunity here, and again, the reason I'm including this is, yes, you can do this with Landsat, you can do this with MSI, the imagers that are really designed just for terrestrial applications, but their revisit time is anywhere from 5 if in a constellation to 14 days. OCI, yes, has a bigger footprint, but can do this every day. And so there's a really neat trade-off here. All right, so mission status, and then I'll wrap this up for questions and let you get back to work here. Right now, we are in phase E, which is prime mission operations. This is going to run through the middle of April 2027. We are expecting to be considered for mission extension. There will be a review later in the year to codify this, but that's to be confirmed. Right now, everything is operating nominally, knocking on wood. That's inclusive of the instruments in the spacecraft. Yes, there have been hiccups. That is true of all missions. We've certainly had our share of them, but everything has calmed, and a lot of that is due to our amazing flight operations team. They've developed a lot of processes to address and recover from or permanently mitigate just about everything that has come our way so far. And of course, this is noting that new issues will inevitably emerge, but we're really, really pleased with how things are going, and I hope you feel the same way. Then as far as products go, and that'll be kind of what I wrap this up with. Right now, all of our required products are available. I'll explain what available means in a second. In this case, we're talking about heritage products, which is effectively what you can get from Modus and Veers. There are a number of advanced ones emerging too. So I hope you check back routinely. And what I'm talking about when I say advanced are the community composition from OCI, the terrestrial products, new coastal and aquatic products, things that you aren't getting from our heritage instruments. And again, one more time, please consider use of the polarimetric data as well. It's really going to be game changing. How do you get the data? Well, right now it's available via two mechanisms. The primary one is NASA's Earth data. I believe that's what you will be predominantly using during FishBase this week. That is a cloud-based system, but it only includes those products that we're considering provisional, which means they've been blessed by the PI and they're on the way to validation. There are also a series of test products where we're still iterating with the algorithm provider, and they're really more robust in the sense they can be produced, but need further investigation. So I'm not sure how many of these are easily available to you for this exercise, unless you want to go to the Ocean Biology DAC and download them, and they come in the form of big global maps. So just as an interjection there, to reiterate what I'm talking about, the data on the OB-DAC website, which haven't made it all the way to Earth data yet, are what we're calling test products. We are happy to distribute them, but they're brand new. They're not ready for full implementation in the search environment from NASA. The provisional products are the ones that you'll find in Earth Data Search and Earth Data Cloud. So those are the ones that have been reviewed, blessed by the PI, maybe not fully validated, perhaps with some errors, but they're sufficiently robust to get into the hands of you all to start your research activities. Okay, so here I'm at, you're focusing only on Earth data. If you do see variations in terms of version number, the most modern one is version 3.1, so make sure you're using 3.1 and not 3. You will occasionally see an NRT label. This means near real time. These are data that are about within a month old. They're only using preliminary navigation and so forth. Imagery is typically reprocessed within 3 or 4 weeks once we get better information, better trending for calibration and so forth. And then NRT label, it gets removed. And Ryan and Eli and I can answer questions about that label, just giving you the idea that there are a couple of flavors here. And then last, if you were to dabble in level 1C spatial, so level 1C data, which is a common grid that we're placing all of our OCI and polarimetry data onto, that spatial resolution is 5.2 kilometers, which is not a native footprint for any of the instruments, including the polarimeters. So sorry, this is getting into the weeds. I just wanted you to have it in the back of your head in case you had questions as you start to interact. And then I will wrap this up with just some housekeeping. This is not a modern slide, but there is a website that we try to maintain as accurately as possible that talks about the good, the bad, and the ugly of all the data from PACE. This is, for example, inclusive of, hey, we're not super psyched with this spectral region, so buyer beware. The idea here is to give you as much information as possible. So that is worth looking at, please, before you get too wrapped up with something that maybe doesn't look right. And then we also have preliminary performance assessments as well. So there are matchups for radiometry, for some cloud products, and for chlorophyll that you can find online as well. If you go to the PACE website, it's very easy to find all of these things. We have met all our requirements. Again, old slide, but I never don't want to share our requirement. We can declare victory. This table is going to be replaced with something that's easier to navigate, but there is somewhere on our website too that talks about all of the different products that we're producing, inclusive of ones that aren't available yet but are in the pipeline. So if you're interested about what's available now, what is going to become available in the coming weeks to months, and what we don't even have an approach for, this is a good resource for that. And then last, if you are interested in field data, there was this amazing, it basically comes in two parts. The first is this amazing field campaign that was 30 days in September 2024 off the west coast of California. It includes high altitude aircraft, low flying aircraft, and ship-based measurements. All of these data have been submitted to NASA. They are publicly available for your use. as are all of the data available from the PACE validation science team. They have a requirement to make sure data gets into our hands within, I believe, 60 days of collection. So it is an ongoing accumulation of field observations. And again, they're available for your use through the CBAS website. Okay, I'm done. That's my half an hour. Last on this slide is just to point out we have a help hub. A lot of what's in help hub is graciously supported through collaborations we've had with Eli and Ryan and others as part of the PACE Hack Weeks. So thank you to all of you. There are tools and resources there that are available to everybody to overcome some of the hurdles that we all face. There's a land users group, which you're welcome to join if that kind of thing interests you. We have a community mailing list. You want to keep informed, that is the best way to do so. And then my final concluding thought is back to the beginning, first things I said, which is thank you for the interest in the mission. I don't think you'd be here if you weren't eager to use the data. Our appreciation for that. I hope you all in your independent work start changing the world, and note that that also helps all of us who build missions. The best chance that we have for continuity, whether it's new missions or extension of OCI, HARP2, and SPEX1 like objects, is through the accomplishments that you all realize. So please be great and don't be shy. I have become very good at sharing your successes with our management so that you look really good the next time you propose to NASA. So, all right, with that, have a fabulous week. I'll try to join here and there when I can, when I'm not shoveling ice out of my sidewalks and driveway. So thanks for the chance to chat, and I hope that timing was okay.
Perfect. Thanks, Jeremy. I appreciate it.